I'm only going to do some examples. We do not have enough time to go into many examples. Let us look at another example. Suppose students came up with this example where we earlier had a sketch. An isosceles trapezium is any cyclic quadrilateral with at least one pair of opposite sides parallel. Let us test it by constructing a circle. We know it is cyclic, so we can start with that. We draw a chord AD as one of the sides. We then choose an arbitrary point on the circle. Then through B, we construct a line BC parallel to AD with a software. And unfortunately, it is slightly behind the caption there, but we can see the slope is the same, and I can drag it to change the slope. This is the beauty of dynamic geometry software. If I draw it on paper, I cannot change it. And then through B, I construct, I've done that already, beg your pardon, and we can simply now complete our quadrilateral ABCD by connecting up the sides. And the question is, does it always remain an isosceles trapezoid or trapezium? Well, I can drag it, as you can see there. I can drag B to change its shape, but it clearly does seem to always remain an isosceles trapezium. No matter how I drag it, I can drag another point there. And notice I can always also get special cases. I can get the special case again of a rectangle. As we know it should, it has diagonals equal. We can visually see that. It has at least one pair of opposite sides equal. This appears to be a necessary and sufficient condition. Of course, it's not a proof, but it gives us empirical evidence that it appears to be a good definition, an economical definition. At the next level, and this is really Van Hiele level 4, where students would now locally systematize, or using the language of Freudenthal, axiomatize the properties of an isosceles trapezium. For example, if we now choose the previous example that we had as a definition, can we now show that the other properties can be deduced from this definition? For example, we are given that it is cyclic with a pair of opposite sides parallel. And then students can now derive the other properties from it by, let me put the labels in there, by relative ease. For example, if we look at this figure, it is given that it is cyclic and AD is parallel to BC, but we know, because it is cyclic, that that angle is equal to this angle here. Not equal, I beg your pardon. Angle A plus angle C is equal to 180, because they are supplementary, it is cyclic. But we also know that the angle A plus the angle B is equal to 180. It is supplementary, and therefore these two angles must be equal from this transitive property. We are almost finished. Let me just move. Must I stop? Okay. We are almost finished. Let me perhaps, with the last slide, focus on the importance of construction and measurement. Let me, in conclusion, make some important points about the importance of construction and measurement. My suggestion would be at Van Hiele 1 to provide students with ready-made sketches of quadrilaterals in dynamic geometry for visualization and seeing special cases. Of course, this is not to replace the concrete quadrilaterals that they can work with, but it is to supplement it. I want to emphasize that it is not appropriate at this level, as I have seen some people do, and even in research, to ask students at this level to construct dynamic squares or rectangles or parallelograms, because at this level they are unable to do it because they do not yet know the properties of the quadrilaterals, nor are they able to see the interrelationships between properties which they need to be able to make the constructions. So this is impossible at this level, so it's best to provide them with ready-made sketches. At Van Hiele level 2, I would suggest that they use the ready-made sketches and to use the facilities of measurement and transformations to analyze and learn and formulate the properties of the ready-made sketches provided to them, whatever software one is using. But it is in the transition from Van Hiele level 2 to Van Hiele level 3 that it becomes important to challenge children to construct dynamic sketches for themselves of the different quadrilaterals. For example, challenge them to construct a dynamic rhombus. And by a dynamic rhombus or quadrilateral in general, we simply mean that they should be able to construct a figure that no matter how much you drag it, it will always remain a figure of that type. For example, one way of constructing a dynamic rhombus would be to start with a circle where we know that the radii are equal, and then to construct all the sides equal, we can construct a circle centered at that point and another circle centered at that point, and clearly the intersection of those circles will produce something which has all sides equal that will always remain a rhombus. Similarly, we can construct a rhombus by constructing diagonals perpendicular and bisecting. For example, drawing an arbitrary diagonal and a segment perpendicular to it, we can reflect that in that diagonal, and then connecting up the points, we get something that always remains a dynamic rhombus, no matter how much we drag it. In this way, they can look at different sufficient conditions for constructing a rhombus. And I think it is very important at this level that students develop this skill and ability to construct and test the hypothesis for developing understanding for necessary and sufficient conditions, and therefore for understanding different definitions of different geometric concepts such as the quadrilaterals. To summarize, dynamic constructions assist the transition from Van Hiele level 2 to Van Hiele level 3, and specifically it helps develop understanding of the difference between a premise and conclusion and the causal relationship. In other words, understanding what an if-then statement really means. And what I'm saying is not new. I was pleasantly surprised in a paper that I read by Smith, which was published in Mathematics Teacher in 1940, where he said exactly the same thing, where he, in a class that he was teaching, he made students do constructions with paper and pencil using compass and protractor. And notice what he says. Pupils saw that when they did certain things in making a figure, certain other things resulted. They learned to feel the difference between the relationships they put into the figure by constructing it and the relationships which resulted without any action on their part. In other words, they learned the difference between the given conditions and what happens. If we go back to this sketch here, Here we constructed the diagonals perpendicular and bisecting each other, but we see as a result of that, we didn't make it like that, but we see as a result of that, all these sides are equal. So as a consequence of that, we see that happening. To finish my talk, I would just like to say, obrigado. Thank you very much.